In this segment, we will be talking about the I/O subsystem. So just to go over the outline, so we've spoken about CPU devices, we've spoken about memory. The next important component of any computing system is the I/O device. And I/O devices have substantially different behavior than the other two that we just spoke about because they're much slower. And in order to accommodate this slowness, the software has to adapt and change its whole design. And so there's certain things that work in the CPU and memory space that do not work with the I/O devices. And so we'll look at that. So first I'll start off with an overview of how different I/O devices interact with the system. We'll look at the principles of I/O hardware itself. So what does the hardware provide? And how is it that different hardware, how is it that we have keyboards from different vendors being able to interoperate with the computing system? Does the software need to change for each of the keyboards, for example? And how is it that a mouse, how does the mouse interact with the operating system versus the keyboard, right? Or what if there are different kinds of printers? Then we look at how the software stack is laid out. So we look at all the way from the user space, how the applications treat these I/O devices, all the way down to the lowest level of the kernel, looking at device drivers, how each of those are individually built for a specific hardware. And then finally, we'll look at an important I/O device known as disks in the next segment. Okay, so let's first start off with the requirements of I/O. So, right, we've learned how to manage CPU and memory. Okay, so with I/O, the challenge is that there are thousands of devices, each slightly different. So in a computing system, there are more types of I/O devices than CPU, for example. And so you need to kind of interact with each of these different types of devices. And the question is, how do you standardize the interface? So standardization of interface is an important requirement. Okay. So standardization is an important requirement. The second important consideration is reliability. I/O devices are just unreliable. There are a whole bunch of issues. There may be intermittent failures where you fail to read the track of a disk, for example, media failures possibly, and transmission errors. You don't want your computer to crash each time an I/O device goes down, right? So for example, a USB flash device fails. You don't want the operating system to crash. So the question is, how do you make software interfaces reliable in the face of hardware that's pretty much unreliable? Right? You also want to make sure that if there are intermittent failures, then you can't recover from those. Finally, I/O devices are just slow, okay, as we already spoke about. So the question is, how can we manage them if we do not know what they will do or when they're going to get done with a certain task? Normally, most systems generate interrupts when they need this kind of service. The question is, how are interrupts going to interact with I/O devices? The common operational parameters typically for I/O devices is either they tend to provide a byte or block interface, where some devices like keyboards, you feed it one character at a time. There are others such as disk and network, which feed multiple multi-byte blocks at a time. And there are some which are like the network, which essentially provide or tape, which provides FIFO access. So sequential access, sorry, in the sense that you cannot seek or look for records in the middle of the I/O device. Okay, so they must be accessed sequentially. There are others which can be accessed randomly, such as disk, a CD, or tape, or memory. And some devices also need continuous polling or monitoring to figure out if the work has been done. Examples of this include things like GPUs, where you offload the work to the GPU and you don't know when it's going to get done. So you need to constantly keep tracking it, or the system needs to come back and tell you that it's done. Okay. So normally, this is just a general layout of I/O subsystems in your system. So most of these I/O devices hang off something like a bus. So in this case, I have many disks hanging off a SCSI bus. SCSI is an interface like SATA, for example. There are also, the most common one is the PCI bus, And here, for example, I have disk controllers. I have more disks hanging off here. I have an expansion bus, which is another bus that's hanging off the PCI bus. And that's controlling my paddle ports for the printer, and then my other serial ports that go through the keyboard or the mouse. Most of these have been replaced with USB interfaces at this point, but then instead of the expansion bus, you have a USB bus that's hanging off PCI or directly plugs into the memory controller. This is one of the reasons for the speed difference. So if you look at it, keyboard can feed at about 10 bytes a second. It's the I/O interface and the interaction of humans with these devices. Right? So, for example, if you have humans typing at a keyboard, you cannot 10 bytes a second is already moving pretty rapidly. You're typing at probably 60 characters a second, right? 60 characters a minute. And so you've got things like mouse, which are slightly faster, but then there's just a whole spectrum of devices with different speed. This is one of the important challenges. So you go all the way from 10 bytes a second for keyboard, right? And Flash typically does like 40 megs a second, right? And sometimes these days you can have double throughput, 90 megs a second. Right? And then you've got things like SCSI disk, which are much faster. Then you have gigabit Ethernet, and then you've got the PCI bus itself, which talks to things like the GPU. And so there's just such variation in the device rates that each of these requires a specific type of interaction. Right? So the system better be able to handle this wide range. The challenge with this, though, is that you can't build a software stack for all of these devices in a uniform manner, because if you have 10 bytes a second, it's not the feed rate is not that high, and so you can possibly live with some level of software overhead. But if you have, let's say, 500 megs a second, right, that's a lot. So per byte, your overhead has to be really small, or the software path has to be really streamlined. And so if you look at even the levels of the software stack in the operating system that need to be traversed, it varies a lot between these devices. So for example, a keyboard, you'll probably traverse a lot of the stack. There'll be lots of layers of software. Whereas for something like a GPU, you try to make it as efficient as possible. And the final challenge is that you don't want to have all of these devices multiplexed to the same software interface, right? So don't have a giant switch case where you have each of these devices being spoken to at the same point. The reason is that, let's say that you were handling a keyboard, right, and you had a really slow path. If you had that, then on some levels, if you had a PCI activity at the same time, that's going to be slowed down because you're handling a much slower device. So if you have these different devices and you essentially queue them up, you could have a really slow device at the head of the queue blocking the rest of them. And so that's a big challenge as well, is to make sure that you don't have such queuing delays in the system. So you got to kind of make each I/O device independent of each other. Okay. So the goal of the I/O subsystem is the following. It's to provide uniform interfaces despite a wide range of different devices. So what you really want to do at the user level is write something like this, where you open a file descriptor, right? So you open the file, and this something could be any device. So it's some I/O device, and the I/O device exports a file-like interface, and then you're reading out from the file and then putting it out onto the screen. Essentially, what we really want is to not worry about whether we're reading from a USB or a disk, for instance, or a network. And the reason is that the code that controls the device implements the standard interface. And so essentially there is the device driver, which sits below at the lowest levels of the operating system that talk directly with the hardware, right? And so this talks with the hardware, and then the user level, we'll look at the stack in a second, but the user level is, there's multiple layers of abstraction between the user level and the device driver, right? And so that essentially controls what the interface the programmer sees, and the device driver takes care of the hardware specifics. So what are these standard interfaces going to look like, and how many do we need? Typically, standard interfaces you have three types of standard interfaces. So you don't want too many of them, because then, it's just going to be too many that the programmer has to contend with. So you normally have just three. So, and three will suffice. So you first have the block devices, such as disks and tapes and media devices, essentially. And they provide access to blocks of data. And on those, you essentially use a file-like interface, so you have open, read, write, and seek. You can do raw I/O, directly reading the blocks off a disk, or you could possibly go through a file system, which we'll look at in the next few segments. Memory map file accesses are possible to improve overall performance. You have character devices such as keyboards, mice, and all the user interface devices, which feed typically one character at a time. And in these, you have much simpler interfaces, just get and put. So you read only the current character, and you put the current character out onto the back into the device, right? And there are libraries layered on top that allow line editing, but in reality, these are constructed based on taking individual gets of characters. You don't really, the system doesn't try to remember what happened in the past. Right? You don't. There's not too much buffering. You just look at the immediate character that's been imported, and then you move on. Whereas compared to block devices, there's a lot of caching, a lot of buffering, because they're feeding in blocks at a time, and you want to be able to hold them in fast memory until the program actually accesses those data. Finally, there's network devices such as Ethernet and wireless. These are different from block devices to have their own interface because you don't necessarily have a file-like interface, and the network itself is more unreliable, and you're running certain network protocols on top of these devices. In such cases, you use what's known as a socket interface, and the most important function is select, which essentially waits around until there's a packet available on the network and then triggers an action in the program. Right? Examples of such usage of such network devices include pipes, which we designed in the past, queues, and mailboxes. Okay. So let's start looking at the principles of I/O hardware. So the first question is, how does the processor actually talk to these devices physically? Okay. So normally what happens is most I/O devices have what's known as a device controller. And the device controller consists of 4 components. There's the hardware controller, which is specific to the device, that knows what the device is about and is acting on it. And then there are addressable memory or queues, which are memory map. We'll look at what memory map means in a second. And these are used for transferring large chunks of data from the CPU to the device itself. And all of these things get transferred through this bus. For example, PCI is an example of a bus interface. And finally, there are a few read-write control registers, and these possibly could be interacted with using a port-style interface where you explicitly know that you're writing to some piece of register as opposed to memory. So we look at port-style I/O and memory map-style I/O a little later. So the CPU essentially interacts with the controller and feeds data out into these registers or memory queues, and then the device controller takes care of operating with the rest of the device. Okay. So the example of this is you got a CPU, you've got a regular memory, which has your memory bus, and then you've got these bus adapters that are hanging off the regular memory bus, which actually interact with this device. And they also have addresses and data so that you can know which location in the device you're actually referring to. And in some cases, this also refers to different devices. So, for example, if you had another device hanging off this, then this would have a separate subrange of the addresses. And all of this feeds out into the interrupt controller, which then interacts with the CPU. So the device is done, it sends out an interrupt request, and then the interrupt controller, triggers an action on the device, on the CPU, to say that the device is done with something that the CPU gave it. So the device controller has registers that control operations. We look at DMA, which stands for direct memory access, in a specific second to look at what kind of information is typically provided. Right. There may also be a data buffer sometimes as part of the controller. This is so, again, to absorb the latencies, the long latencies that you may specifically encounter in some I/O devices. And the CPU's goal is to essentially communicate with the controller and the registers and the data buffers. Okay. So let's look at the memory and the I/O space. Okay. So essentially, there are 2 ways of communicating with the I/O. So if you have a separate I/O space, so this one is port-based access to the I/O devices. Okay. So There are two ways of dealing with this. One is you have your regular memory space, which has addresses 0 to, for example, in this case, let's say 4 gigs, right? So if you have 32-bit address space, you could have a separate I/O space, which again starts from 0 and then goes up to some number based on how much space you dedicate for your I/O devices. So in this case, if you want to access this specific location, you would have to reference it using the number 0 and then have another flag that indicates that it goes out to an I/O device. So the 0 indicates that it's an I/O device. Right? Typically, this is done using a port instruction. So port says, I'm going actually to an I/O device as opposed to memory, and then you feed it the address of the I/O device. So, okay. Normally, a simpler way to deal with this is if you merge these. So you could have the case that essentially you schlep off a part of the chunk of memory address space and dedicate it to the I/O device. This is what systems like Windows do, essentially, where based on which address range you're referring to, for example, let's say between address range 3 to 4 gigabytes, right? These are all I/O devices. So these are not the system cannot use these for memory. So anytime there's an address access in this range, the system automatically knows that it needs to go to an I/O device. Okay. So in this case, you have separate I/O and memory spaces. Memory mapped I/O is if you map device memory into CPU memory, and each device memory is assigned a unique CPU memory address. So this one is an example of a memory map, right? And this one is the example of the port style interface. And you could have hybrid systems where the data buffers, so these are hybrid. So this is the case where the data buffers are in memory and the lesser frequently used control registers are in a separate I/O space. Okay. This is so that for latency concerns, you want to be ensured that if you know if certain access needs to get to a certain register in the device by by certain latency, then you could do that because now you know that it's an I/O access. If it was just a memory access, then you would not be able to do that. You may do things like buffering. But there are things like block transfers, which would be really inefficient in this manner. And so if you frequently interact with it. And so in such cases, you would rather prefer to consider it just like memory and let the system take care of it. So the way this whole thing would work is each control register is assigned a port number, okay? And normal CPUs provide a special instruction known as in and out. So in is if you want to read from the register, and out is if you want to put something out onto this register. And the minute you use this, you use the port number, and the CPU automatically knows that you're not referring to memory, but you're referring to some register on the I/O device. And if you have memory mapped, so then the memory region is the I/O part is mapped into a memory region, and so the I/O control registers are mapped into memory addresses, and then processes can directly interact with the memory mapped system. So all registers are mapped to the memory space. The memory map will have a block of addresses that actually really correspond to registers on the I/O device rather than to locations in memory. So you've kind of given up certain locations in memory and said, I'm going to actually try to, anytime an access happens to this address, actually really forward it to the I/O device. Okay. And when you read or write from the memory region, the system automatically takes care to forward this information to the I/O control registers as opposed to real memory. And it's all completely transparent to the system. An example of how this whole thing would work is, let's say you have a display controller, such as something that puts things out onto the monitor. So you typically have your OpenGL or graphics command queue, you have your display memory, and then you have your commands and statuses. Okay, so these are your registers. So all of these are mapped into the physical address space at different points. Okay, and essentially, once this has been set up, the hardware sets up certain flags at different points to say that anytime an access happens to these addresses on the bus, these get forwarded to a certain I/O device, in this case, the display controller. And so in this case, we've mapped, for example, the command queue between 10,000 and 20,000, right? And so we've mapped it in this range, and so anytime an access happens to this address range or this pointer, then it gets forwarded to the graphics command queue. Okay. And so writing to the command register itself may cause the hardware to do something such as rendering, so it may be certain specific flags, so these may be addressed with bytes, while these may be addressed with blocks. Once it's mapped into memory, the data structure that you do try to use depends on the hardware as to what interface it's exporting and what the software does. The reason this memory map is also useful is so that you can use virtual memory to essentially control which processes get access to this piece of memory. So if you don't map it into certain processes page tables, then that process does not get direct access to this I/O device. But then if you do it and you trust the application, then the application can really improve its performance by directly interacting with the I/O device as opposed to going through layers of OS abstraction. So the big advantage with memory mapped IOs is one is that now you're starting to think of IO devices as as just memory, and you're letting the system take care of forwarding data to it, which means that you don't need special in and out and special instructions anymore. You can just treat them like you're accessing memory. And now you can write these lower level pieces of software that interact with the device in C or higher level languages rather than an assembler because you don't need these special instructions. And every instruction that can access memory can also access these control registers, right? So you don't need special way to separate out control registers from control register operations from memory itself for the data buffers in the I/O device. They all look the same, just based on what address you write to. And finally, you can use virtual memory mechanism to protect the I/O from user processes. So you can map it into the kernel space and then control what I/O devices get mapped into which processes. The big disadvantage with memory mapped I/O is, first of all, you need additional complexity in the OS. So this is arguable. It's not necessary that it's more complex or it's just different. It's just different from the port interface that you need extra layers of abstraction. So, for example, you cannot cache things like control registers. Um, because if the data from the control register is cached and you make a write to it and you treat it like memory, it does not get reflected in the I/O device immediately. So that's my point behind some of these control registers need to be updated, and they may not necessarily be. If they are memory mapped, then you have to deal with the fact that they shouldn't be cached. And so you got to disable caching, and so systems need to provide that support. All memory modules and I/O devices must examine all memory references just to figure out whether the memory access pertains to them or not. So they need to do a